Okay, let's now talk a little bit more about the graphics APIs and shading languages we use in this course. Again, let me reiterate that I'm not teaching you graphics API syntax or any of these things. This is something you need to practice on your own until you're fully grown. And you can then basically work out most of the problems you come across in graphics APIs by probably Googling. I'll again tell you a few of the caveats in OpenGL in this lecture and a little bit of the historic background. The one thing you probably need to be aware of is that there are several versions and one or two conceptual changes in the history. So if you find random code on the internet that might well be written in a different concept, which doesn't run anymore in a program you probably write in the more modern environment. So this is the only thing you need to be aware. But really, well, let's dive into this and let's have again a little bit of a recap of what's out there. So there are low-level 3D APIs, really not programming languages, but APIs. So like what I mentioned, OpenGL, ES, DirectX, and so on. And we are specifically talking about OpenGL, and in the coursework we're using WebGL, which is basically the same with a reduced instruction set. So very important. OpenGL is a low-level graphics API specification. It is not a library. It's not something you include in your program and then execute functions that are implemented in that very same language, doing specific things encapsulated from your main program. The interface is platform independent. So the interface is always the same. You always ask OpenGL the same commands and the same drawing API function calls and these sort of things. But the implementation itself is very, very platform dependent. It depends if you run that in Windows or in Mac OS or on Linux. It's very platform dependent. The interface is platform independent. The implementation is platform dependent. The interface defines an abstract rendering device and a set of functions to operate on this device. And it does this in a very strange way. It is an immediate mode API. It draws whatever it gets immediately. It's a real-time engine. And this is kind of different from what you're used to in other programming languages. There is no concept of permanent objects. Everything is tailored towards performance, performance, performance. And the interesting thing perhaps is that OpenGL on its own is designed as a state machine. So it is not really an object-oriented programming language. Well, wait, yes, it is an object-oriented programming language, but in a very, very strange way. And the execution mode is immediate mode on a state machine and everything, all of that just for performance. So the platform itself, like your operating system, provides an OpenGL implementation. It is a part, the implementation, yeah, it's part of your graphics driver. So your graphics card venue or whatever you have in your laptop will provide that implementation for you. And the runtime library is built on top of that driver. And you initialize this API usually through import commands or includes, depending on your language. In Windows, usually the key header, the key kind of module you would include is called just OpenGL. But there are some variations, like in Windows, most of the functionality of the extended functionality is implemented in something called WGL. Unix is GLX. Mobile devices is EGL. And somehow when the problems start already here, because if you find some code for mobile devices, it will not necessarily run on just purely Windows. You need to fall back to the kind of most common platform independent implementation of specification of OpenGL. And as I said already, it's a state machine for high efficiency. Now this is probably the most important diagram you'll see on these slides today, representing the flow of graphical information as it is processed from the CPU to the frame buffer, so going from here to here. And there are two pipelines of data flow really. The upper pipeline here is for geometric vertex-based primitives, and the lower part here is for pixel-based image primitives. So texturing combines the two types of primitives really kind of together somehow. And there is a, well, if you want to know all of the kind of nitty-gritty details of these sort of operations here, it's just a different view of what we did in the conceptual level in the last video. There is in the OpenGL reference manual, the so-called blue book, there is a large poster about that, which shows this diagram in very much more detail. So how to write an OpenGL program, and this is usually always the same recipe. You need to somehow set up a render window. For example, provide some context providing libraries, and there it already starts to become complicated, because just to get the rendering area, you need lots of language specific, operating system specific libraries that provide you that interface to your kernel. So in Linux, you would have something like LUT as a very simplistic way. There's Qt, browser SDKs and so on there. Every browser, in fact, currently is just a render interface for efficiency. And that you could also use as a kind of rendering context. And then you need to set up and initialize some very basic functions. You need to set up what that rendering area represents, so the viewport. How do you look inside your scene? You need to set up the initial model transformations. You need to set up file I/O, read object files, textures, shader files, all of these things, and then define the frame generation. How often, how is it, what function is called for every update, every frame you want to generate. Define what happens actually in every frame. That is something you need to define in your application stage in OpenGL. And this diagram here illustrates the relationship of the various libraries and window system components. Well, generally, applications which require more user interface support will use a library designed for doing exactly that. For example, for buttons, menus, scroll bars, such as, I know there are several of those, Motif, Windows 32 API, Qt, all of these sort of libraries usually come also with a kind of sub part that gives you a rendering area. But all of this button stuff you don't want to do yourself, you want to ask one of these kind of libraries. To build prototype applications, so one which don't require all these bells and whistles of a full GUI, you may choose just a Qt or GLUT simple environment instead, because, you know, really just of a simplified programming model to write one file of graphics commands. I mean, it doesn't really need, I don't know how many gigabytes of additional libraries just to run this render screen. So yeah, but this has always been a kind of problem with graphics. If you look at what ShaderLab Web, so the environment for the coursework actually downloads on Java libraries, and well, this is also JavaScript libraries. So then this is also quite surprising how much you need to do very, very, very simple graphics program. So all of our discussions will be presented in will base on more or less C. So for C or C++, there are a few required elements which an application must do. So the header files here, they describe the basic API and I/O infrastructure here, and libraries are operating system dependent. So here you need to know what you need to do. Qt is probably the most operating system independent variant here, so you would just include Qt OpenGL and you get everything you need to run GL commands. Still, it has more overhead. So Qt is also not completely free, so it comes with a lot of overhead. You need to download several gigabytes to get just the framework. Or well, the alternative is browser-based graphics engines, and well, probably our environment, what we provide. That's one of the reasons why we provide this environment, because it's otherwise quite a pain for you guys to run all of this overhead and compile everything yourself until you get to the point that you can actually solve almost coursework tasks. That's not the point of the exercise. Okay, OpenGL, very basic concepts. most importantly, there's a context in which everything runs. Context is usually linked to your render area. There's one context in one application. You have resources, and there is surprisingly an object model with objects, object names, and bind points, targets. So this sounds a little bit strange. So let's look a little bit into what the individual parts are. So the context represents an instance of OpenGL. So this is your user mode driver thingy, which you can give commands, and the commands will be handed down to your kernel and then eventually to the GPU. So a process still can have multiple contexts which can share resources, and resources like textures, for example, or objects. And the context can be current for a given thread, which means it can be the one that's used in a current processing thread. And there's a one-to-one mapping really. Only one current context can there be for one thread. One thread can't have more than one context that's currently in operation, and the context can only be current in one thread at the same time. Okay. So you need, if you have several render windows, you need at least one thread per each of these render windows, and then this thread operates in one on one individual context. And OpenGL operations only work on the current context. You can always call OpenGL operations, but they will always apply to the context that's at the moment current. Okay, so this is already, the state machine is showing through, right? So you have activated that current context. It's current right now, and then I can push out OpenGL commands to the kernel, and the kernel will apply to whatever is currently in the state machine. So resources act as sources of input or sinks for output, for example, buffers or memory areas, images, state objects, textures. All of these are resources in OpenGL speak. Buffer objects, for example, are linear chunks of memory. It's just really an alloc. And texture images, they are also linear chunks of memory, but texture images can be interpreted slightly differently by hardware, specific hardware units. So you can have 1D, 2D, or 3D areas of texels, which can be used with specific texture sampling hardware, which also gives you linear interpolation capabilities. Very, very powerful in graphics programs. So the OpenGL model is surprisingly object-oriented, but in a very strange way. So object instances are identified by a name. So basically it's just an integer you get. So the way this works is you need to define a reference to an unsigned integer, and then you request an object from the state machine, and it generates that object for you and gives you back something like a number plate, a magic number that identifies that specific object. And commands always work on targets. So each target has an object currently bound to the target. So you always need to make sure that you activate certain things before you issue that command, which will then be executed on these specific objects currently on that stack. Again, that's the one command that will work with all of these objects. So it's not like you have a function which you pass on the objects it should process. No. You have to activate all of these things, lay on your stack, and prepare everything before you run that one command. So the object-oriented bit comes from this. So the targets here, the types, right? So this is the type I can pass on. And I don't need overloaded functions in this context then if I have this sort of target system, and the commands are methods of your objects. So well, this is what I just explained. You really have to always put things in place before you execute things, except shader objects, which are program objects. So these you need to compile, and basically they're part of your graphics pipeline. And you don't need you don't always need to prepare everything for shaders. Some commands only work on shader objects that are kind of global in the state machine. It becomes a little bit messy and unclean here, but that's how OpenGL works. So buffer objects, I already said, these are objects in which you can store memory, anything you need, and can be, for example, used to store vertex data or any data retrieved from images or frame buffer. So if you have loaded your whatever object model, you can put your vertex data directly on GPU memory and define a buffer like this. So to set that up, you need to bind it to the current context. So you would say GL bind buffer and then which buffer you want to bind. And then you have immutable objects like GL buffer storage, where you then stream in all the data you want to stream. You can also make it mutable here. So it really depends on the implementation and what you want to do with it. It has a lot to do with what sort of memory structure you would use here. Lots of that has highly efficient caches, and if you know already from the beginning it's a read-only, then you would of course prefer memory that's better buffered, that has better caches, so that everything is quicker. Everything is optimized for real-time execution. So it's a program example. So what I do here is to declare a unsigned integer. This is really just an integer, despite the kind of clarification type here. But it's an integer, and then I ask OpenGL in the current context. Note there is no kind of reference to this object. I just ask GL gen buffer. I want to generate one buffer, and the reference where I want the reference stored to this object, the number stored is handed over like this. Then I bind this newly generated buffer as an array buffer. So I let the bind buffer know there's an array buffer, and then I hand over this number plate. Say immutable object. I just add this data, whatever it is, vertex data or something, in that array buffer. I have to interpret it as array buffer. Unbind doesn't really exist. If I want to explicitly not bind something anymore, then I have to bind the 0 object, but that's optional here. I don't really need to do that because the next object will anyway define a new state in that state machine. And then later on, so imagine there's some other code here. Later on, I want to read that perhaps again, so I bind that buffer again in the state, and then just a GL draw array here and say these are all triangles in this buffer, and I know there are 33 triangles in this buffer, and start with the first triangle here, a first entry in that array buffer. But you see, nothing is telling draw arrays here that it needs to read from my buffer. That has been bound before to the state machine. So very strange, right? But you need to get used to that. Then it's becoming reasonable somehow, but it's still very difficult to debug because of that state machine nature. You actually don't get errors from the state machine. You always need to ask the thing if there is something wrong right now, and then everything, you know, real time. So it's sometimes quite difficult. If you want to get rid of one, so basically a free or delete, you just delete one buffer, and you tell it that reference. So in OpenGL, we have specific primitive types, and primitive types really means how I would, for example, interpret a number of vertices in one of these array buffers, right? These are just 3D coordinates, a list of 3D coordinates. And in this case here, they're interpreted as triangles. So it's always 3 of them, triplets of them form one triangle. So it's triangle, 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 triangle in that list. And OpenGL can do these primitives. We can do just points or lines or a line strip or a line loop, or this whole thing defines a polygon. Then triangle strips, conceptually slightly more difficult, but it just means all of them are connected. Individual triangles, a triangle fan where everything comes together to the first one. Quads is also possible, or a quad strip where each quad consists of 2 triangles. And this is also programmable in the tessellation shader if you use a shader model most advanced enough for this. So with the triangles, it's getting, well, you just need to be aware of certain things, but that is conceptually probably, or that's probably the one thing that's used most with these in the context. So triangles are always counterclockwise defined. So if you have your array stored with vertex coordinates, then it's always counterclockwise 0, 1, 2. And then the next is 3, 4, 5. It's always counterclockwise here. And if you define it as triangle strip, then you have the first counterclockwise, the next clockwise, the next counterclockwise, and so on. And that's how you define your triangle strip. And this is just the only difference is then the keyword you give it, and then it will interpret your array data in the one or the other way. So when that pipeline is configured, you can just issue these drawing commands, either like this, you wouldn't probably do it like that anymore, but you set the color state here, and then you issue the vertex, and then that command goes really out as a assembled graphics command to the graphics. That whole thing here, this goes out to the graphics hardware. So here, this is then assembling really a list, like an array list, with GL begin and end of, in this case, interpreted as triangle strip. So this is really, really old school OpenGL. Probably you would really do it more like this, where you have all of them defined in array buffers. In fact, in the newer OpenGL shading models, you have to do it that way. There's no way you could do anything like this. And yeah, this is what we had before. So we just draw whatever is in the currently bound array buffer. Okay, the draw commands here, so this is just one example, but there are no overloads here. The overloads are coming in individual function names here, and they have a scheme. So what you usually get is the function to how many components it's applicable to, 3 or 4, what data type it is, byte or float or any of those, and what, if it's a vector, for example, or you can also have a buffer object already there, and you can have a pointer to some system memory location where you can directly operate like this. But so in this case here, this is just a pointer to a memory location, and it will be interpreted as a vector of 3 elements in float. So that is all encoded in the name of the function. It's not, I think it's not pretty according to most of your standards, but that's the way OpenGL does it. So yeah, this is just a pseudo example. You can study this. This is a very primitive one, but you would really just have things like initialize all of that, set a few pipeline parameters like what's your clear color and clear the depth buffer, and then probably start rendering and say, okay, this is what we do then all the time. Very old OpenGL. You will also probably see sometimes in OpenGL code from the internet these kind of matrix stacks, and before shader model 4, usually what you would do is to define a shader transformation stack, which are all the transformation matrices we discussed in earlier videos, just put on a stack. So they will be, if you evaluate that, they will be, if you pop them, will be always multiplied together, which is a quite nice concept if you want to have them quickly processed and have transformation states which you can push and pop through. Is not recommended anymore, and after shader model 4 you wouldn't do it like that anymore. You would have to program it in shaders. Okay, this is how you do textures. If you want to load a texture in your texture unit, you have to set a lot of parameters. For example, what happens at the edges, how do you interpolate between pixels if you don't land spot on your pixel coordinate, which is always the case, and then how your memory area is actually encoded. That's in this case is RGB in an unsigned byte. Data type. We'll talk about textures a bit more, but this is basically how you would load that entire texture into memory. And then if you want to use it, you bind the texture to a texture unit. So here, this texture unit 0. Do something with this texture, read it, for example, in your shader, and then you can render the teapot here, for example. There's in GLUT, this is a specific function that gives you a teapot. And in this case here, it will render the image that you have loaded here on top of the teapot. Okay. And then if you don't want side effects, you unbind it with 0, but really, you really don't have to do that. Okay, so shader OpenGL 4 is where you replace most of these fixed function things by programmable bits. So you have to do all your transformations in shaders, all your texture lookup in shaders. There's very little left of the traditional old fixed function pipeline. Yeah. So really the OpenGL 4 pipeline added another pair of shaders also here, which work in tandem. So we consider it basically a single stage for supporting dynamic tessellation control here. So this is what I earlier in 3.2 showed, this tessellation control and tessellation evaluation shader. And they were added in OpenGL 4. The current version of OpenGL 4.3 includes some additional features over the 4th pipeline, but no new stages here actually. So you have all of that programmable now. Vertex shader, or whatever happens with your texture tessellation. Geometry shader is programmable, how geometry is interpreted. The rasterization, interestingly not. That's the only thing that's still hard-coded. If you have a list of primitives, that's rasterized no matter what. And then fragment shading and blending, that's all programmable now. Good. So very modern, so OpenGL graphics programs do basically the following. You create always shader program, create buffer objects and load data into them, and then connect data locations with shader variables. This is also what you do in the ShaderLab framework, but still in the order context, so it's a bit odd in ShaderLab framework, but in ShaderLab web actually, but it's that concept. And then you render. You prepare everything, order data, put on the GPU, and then you render. So the shader objects really are part of your pipeline. So they are compiled during the runtime of your OpenGL program. So it means OpenGL comes with another compiler in your program. So you might have a program compiled from source that has another compiler that compiles shader code during runtime. The syntax is C-like. You have probably seen a few of the examples already. And what you try to build is a program object. So a whole pipeline consistent of small shader pieces. So shader objects are linked together during runtime actually. How this works in OpenGL is that you create a shader with this GL create shader function, and you call it, tell it that it's a vertex shader. You want a vertex shader. You set the shader source with GL shader source. So this can be text string or read from file or whatever you like. So you set it into the current state. You compile the shader. You need to query for errors here. You do the same thing for the fragment shader. Fragment shader course, compile, check for errors, and then you say create program by attaching these shaders. So you create the program first, no shader attached yet, and then you attach the compiled vertex shader object and the compiled fragment shader object, and whatever you have, tessellation shader, geometry shader, and so on, comes all in here. And you attach this to the created program, and then you link the whole thing. Check for errors, always. And the errors are terrible, so they are not very informative. So then you can, as soon as you have that linked without any errors, you can use that whole program before you render any objects, or in our case, usually it's just, you use the program, and in ShaderLab Web, for example, it's just rendering the teapot most of the time. Okay, data types, they are the usual C-style data types. We have floating point, integer, Boolean variables. They are built-in vector types, which is pretty convenient if you have if you work with geometry. So you can do 2-dimensional, 3-dimensional, 4-dimensional vectors, integer vectors, Boolean vectors. You have matrix types, 2-dimensional, 3-dimensional, 4-dimensional. You see, 4-dimensional homogeneous coordinates is the kind of most complex you can do in here. Everything is tailored really for what your hardware can do, because your hardware is also optimized for 4x4 by 4x1 operations. There are texture sampling special units, which are sampler 1D, 2D, 3D. This is just linear interpolation between sampling. Texture samplers. You can do cube for cube cube map sampling in environment maps. Construction works like in C. You define type variable name equals type like this. So you have constructors like this, or you can also do directly back 3D. It's this an anonymous function. So standard C and C++ arithmetic and logic operations are available. The operators are overloaded from matrix and vector operations, so you can do probably mathematically unclean operations, but you can kind of combine and multiply just by using the multiplication operation here and then multiply the vector to the matrix here, for example. And the thing is, it is not MATLAB. So it will do it no matter what, and do it always that you get a result. All right, so you need to be careful with the order here, because sometimes it will be, so that way it will be interpreted as a 1x4 vector, and that way it will be interpreted as a 4x1 vector. It doesn't really matter, but you need to be a little bit careful here. It will be executed all the time. MATLAB, for example, would tell you that's not possible, or any other reasonable trigonometric geometry library would tell you that you have to be careful here. So for vectors, you can use either the normal array definitions like 1, 2, 3, 4, whatever you want to put in here, indexing. You can also use swivel operators like these, X, Y, Z, R, G, B, A, or STPQ. They're all doing the same thing. They're just accessing the first, second, third, and fourth component. It's just to make things more readable and more clear, that you can distinguish if this is now position or color value or texture related coordinates. So what you can do is you can really access them individually. You can say, okay, this is the first or the second element here. Actually, it's like C indexing. 0 would be the first element. So you can do it like this, or the equivalent, you would have y, v.y would also give you the second element. v.g would also give you the second element. v.t would also give you the second element. It's all equivalent. It's just for readability and make it more convenient, so they refer to the same element. And also very efficient operations are possible, like Swizzling, where you can swap the order of them and just say, okay, these two are now swapped around, and this is really just a 1 clock cycle memory operation in cache probably. So this more or less comes for free. And your GLSL, there are in-out qualifiers. This copy vertex attributes, for example, and other variables to and from shaders. So they're before all the functions come in. So you would say, for example, that into this shader component, you would have the vector2 texture coordinate coming in from the previous parts of the pipeline, and your linker will tell you if that is not matching whatever comes out of the previous shader. So that is a common source of errors. For the shader, you can then also define what comes out, like in this case, Vec4, which is a very common one color for the fragment shader, for example. Uniform variables are variable qualifiers that define variables that are set by the application stage. So for example, your time is a common one. So if you have uniform flow time, then this has to be set, has to be found by the application stage in your shaders. You need to be aware of them and then set it either like time you would update every time you render a frame. A rotation probably every time you have some sort of mouse interaction, or it depends really on what you do with it. All of that has already been done for you in the web interface and for the coursework. So you don't need to write this application stage code. You can access it in that way, and we did some magic to automate the process. If you write in uniform float some whatever variable, it will pass that and give you a way to set that or connect that to application stage variables in the interface. So the control flow is as in any other language. We can use if and if else and while and do while and for loops. We can also do these kind of shorthand expressions. So all of that works pretty much like the programming languages you know. Inbuilt math is strong. So there are entire cheat sheets about what's available, but the basic stuff is all there. Square root, power, sine, cosine and so on, and but also some basic graphics functions already, something like length and reflect. And reflect is already implementing a kind of reasonably complex dot product operation, but it does it in one go. So this is highly useful if you do graphics graphics computations. So older GLSL will require you to set variables like GL position as the output for the vertex shader instead of the out qualifier. So there in GLSL, for example, in GLSL and OpenGL 1 and so on, you would need to set GL position as the actual output. Or GL frag color as the output of the fragment shader. We'll need to do that in the coursework framework because WebGL does not allow anything else than GL 1.2. Right, so in the desktop version of the framework, you would find the in and out variable qualifiers. Okay, so this is just the basic anatomy of how a GLSL shader pipeline looks like. You can define what version you want to use. Please don't do this in ShaderLab Web because ShaderLab Web only accepts 1.2.0, right? Not 4.0.0. But the important bit is here. So here we define matrix 4 as a uniform variable. So this has to be set by the application stage. There won't be an error if you don't set it, but you don't have that what you expect then in there. You can do things like these layout qualifiers. They are very optional, but they only if you want to optimize things around, they tell you where in the memory buffers that are in between the stages of your graphics pipeline you expect this variable to be found. So you can do something like invex3 here. So this is really for OpenGL 4. If you do that in ShaderLab Web, it will probably throw an error. And here I can already define what sort of output will come out. And here in this case, this is a vec4 that can be anything, color or position or angle. So in the coursework framework, that is actually GL position and GL frag color. So this is GL position, and this is already hard coded in here. So you don't need to define these in the coursework framework. You only have these kind of uniforms, and you don't need to define this here. And then you have a main program, and this is a main function that will be executed on every single object in this context. I was just thinking if this is a vertex or fragment shader, but you can't really tell here. So this will be either processed on every vertex in the vertex stage or fragment in the fragment stage. So the vertex shader processes each vertex, and I've already mentioned that many times, that the vertex shader is processing vertices in the range of millions, and the rasterizer produces fragments, and the fragment shader really processes all the fragments, which is in the range of probably billions. Yeah, I'll probably skip this because really these are the ones you need for the coursework, GL position and GL frag chord. It's not ideal, but that's all we can do with current WebGL. Probably we can update this next year when WebGL supports higher version numbers of OpenGL actually. So this is how a vertex shader could look like. A main program is processing all the data that comes in. I've defined what data comes out here, so it outputs a data structure with a vec4, vec3, vec2, and vec4 inside. This is all the payload that comes out here, and this is really handled by the rasterizer quite well. And the rasterizer gives us then interpolations, linear interpolations of all of these between the vertices of our geometry stage here. And this is something you find a lot. This is something you find a lot in modern shaders. This is, you have to do your model view projection transformations in the shader. So this is the model view matrix. This is a projection matrix. This is the normal matrix. This is basically just a model view matrix without the translation components as a mat3. It's just used for the transforming normal vectors. Okay, and then, you know, position is just projection matrix times the transformed vertex in camera space. So this is really just doing camera space. This model view matrix times the vertex in world space coming in. Then the position in cam space, I just said it here. This is redundant, actually. We normalize this here because why not? Normalization is always good in shading. So this is just really for the normal vectors. So all the normal vectors that come out here again are again unit vectors. But this is really only important if you do lighting, which you hopefully do a lot. Color, it's just red. Texture colors doesn't matter, it's whatever comes in, and projection matrix then projects it to camera space. So the rasterizer can then do its job directly on the projection plane. The fragment shader in this case here does nothing else than just outputting whatever the fragment color stores in its payload. And what you could do here, for example, is doing Phong illumination and approximate the kind of light thing here, like the specular highlight here and the reflection of that light in my teapot. But this you do in a later exercise. Okay, this we already discussed. This is what comes afterwards, after the fragment shader. It's really, that's again partly a topic for the operating system and the operating system's business. If you want to know more about OpenGL programming, first of all, Google, please. Stack Overflow is a great source. But the key takeaway message is probably really be careful with the different versions. Always be aware what version you work in and what works and doesn't work in the one or the other version. So you cannot easily copy and paste code from the internet for your graphics applications, except you know what you do. And there are lots of manual books. They're all free on the internet, so you can just go GL Programming, Redbook. Redbook is the syntax and everything. It's old, but still didn't really change. The abstract interface didn't change, so you can read everything about OpenGL there. And for all the subtypes like OpenGL ES and so on, there are always these kind of open API books which you can read. And the textbooks are reasonably good, really, as a reference at least. They're really good if you do any advanced programming here.